Hey guys, and welcome to a new video. In this video here, we're going to talk about the particle filter. So we're going to of an around and also localize where is that in the environment. But first of all, remember to join Discord server. I'll link to it down in the description here. You can join the channel, chatters about computer vision, deep learning, AI, and so on. You can also become a member of the channel if you want to support the channel with a small monthly fee. Everything will go create more and better quality content here on the channel. Also, if you're a member of the channel, I can give you some help and some guidance with your own problems in your own projects and so on. So thank you guys. So first of all here, we're going to talk about what is the particle filter, what is the pipeline, and how does the particle filter work. So first of all, the idea behind a particle filter is that we actually just spawn some random particles. We can see a flowchart over here of the pipeline actually using a particle filter, and up here to the right we have an example that we're going to go through on the next slide as well, so I can give you like a more intuitive way of how it actually works. But the idea here is that if we for example have a robot in the environment where we have attached a lidar on top of it, then we'll just say send all these laser beams here. We'll get the distance to all the different kind of points or all the lasers sent out from our lidar, so we just get information about our environment. Then we're just going to spawn some random or like some artificial particles around on the map as well. And then from those readings, then we also apply a lidar on top of that, and then we're going to get those readings as well, and then we can compare, and we actually just get our landmarks. So let's say we're driving around in the environment, then we know where are the stop signs, where are the traffic lights, and so on. So those will be our landmarks. Then when we're driving around in our environment, it could be, for example, from a camera, then we can measure these different kinds. We can see how are we actually, like, we're looking at some landmarks in the scene. How are those like related to the landmarks that we have from our particles? Then we're just trying to match our new measurements with the particles and the landmarks that we got from the particles. But here we're just going to get really simple. We're just going to start really simple. So we're going to initialize some random particles around here on our fairly simple map. We just have a couple of different rooms. We have a robot that we want to track down and localize in our environment. So here we can see the blue beams here from the robot is actually like the robot's lidar, and then the green like lines here are actually like the particles lidar scanners. So then we're going to initialize the random particles around on the map. Then we're going to move the particles with the robot's odometry. So we need to set up the odometry for the robot. We can have some slippery and so on the wheels, but we're just going to try to move a particle with the robot's odometry so we can localize where is it, how are the measurements, the landmarks changing in the environment. We can also add some noise for the odometry, like for example, say we want to take into account the slippery on the wheels. It could be like the friction of the wheels and whatever we're driving around on. And then we're going to associate the lidar data with the landmarks from the particles. So we get landmarks from the particles, what we see from the particles that were spawned randomly around on our map. Then we're going to associate our lidar, which is the measurements from our robot, with those landmarks. We can also add some sensor noise. If we have some sensor noise on a lidar, it is often seen that we have a lot of sensor noise when we're dealing with real life sensors. It could be cameras, lidars, some other different kind of distance sensors, and so on. And then we can actually like update the weights with the associated data. So we're going to match the data, then we can see what are the good data, where do we actually like have particles spawned around, where are the similarities between the measurements and also the landmarks from both the particles and the robot. Update the weights like based on those particles. So let's say a particle that is seen like close to the same as the robot, that this is actually like a really good particle that is spawned, and the robot could actually like maybe be in this position. It could be also be in some other room where we can see something similar, but we know that these two particles could actually be really good. These measurements is kind of the same, but they're still in two different rooms. But then we're going to update the weights with our associated data, so a higher weight if the measurements are better or like the landmarks are closer to the measured data from our robot. Then we just update the weights. We just keep like, so the greatest weight is also where we actually think that the probability of the robot to be in is the highest. Then we're going to resample with the best particles. So let's say we have a robot, we have two particles where the landmarks matches good with the measurements from a robot. Then we say that these two particles here are really good. And then we're just going to resample some particles around those two particles that we just found. They have high weight, so we're just going to like sample particles from those again. And then we just move on loop here. We move the particles with robot odometry, associate the new lidar data with the landmarks from the new particles. So these are actually the really good particles. And then we just keep doing this loop here over and over again until we actually like localize and find our robot in the environment by just associating the data from the robot, so the measurements from the lidar, with the landmarks that we get from our particles that were spawned around in the environment. And then we're updating those particles based on what we're actually seeing in the environment when we're driving around, also updating with the robot's odometry, so we get a better understanding of where our robot in the environment. Here we're just going to talk about some of the different kind of applications that we can use particle filters for before we're going to jump into the code. Into some code, we're going to see a really simple example of how we can set up a particle filter, and also it's basically just how we can set it up, initialize some starting conditions, do like weights, associate data with each other, update our particles with some weight, and then we're going to resample and do it over and over again, try to localize some object or like some robot that is moving around in some environment. So it can be used for different kind of like tracking and localization applications and projects. It could be robots driving around in environments, warehouses, and so on, but it is also just dynamic systems in general. We can use it for a lot of different kinds of things like self-driving cars. If we just want to track something, for example, like an object camera, we can also use particle filters and so on, like in computer vision and etc. So here, the last thing that we're going to see is actually like the results from the particle filter before we're going to jump into the code, see a really simple implementation of a particle filter. So this is a bit more advanced particle filter, but just to show you like how it works and what it can be used for. So first up here in the first figure, or like in the first map, we just have these particles here sampled randomly. So we're just going to spread out a number of particles that we choose for, by itself. We're just going to spawn them here in the environment, and then we're just going to take in the measurements, get our landmarks, and then we have the blue lidar scanner here from a robot. Then we're going to match those with the green lidar range here that we get, which is actually like a landmark, and then we try to resample around that. So over here to the right, we can see here in figure B, we can resample after some iterations. So here we actually like just resample where is the probability highest for a robot to be. So we see something like over here to the right, we get a lot of different kind of like good measurements or like good particles over here to the right. We also get some particles here around the middle of our robot here. But then we can see again, we just keep iterating, we keep associating data with the landmarks and the measurements, we update our weights, and then we just resample. So here we can see down at the bottom, the robot's position is almost localized. And then at the end here, at the last iteration, we can see that we have now actually like localized our robot. We can just keep on sampling, trying to track down the robot when it's moving around in the environment and so on. So this is just after some iterations. So we're just going to run a for loop or like run a loop here. It could also be a while loop until some condition has happened. And then we're just going to run it for a number of iterations until we'll have localized our robot in the environment. So now we have an intuitive understanding of like what is the particle filter, how can it be used, and what is the pipeline. So what are the different kind of steps when we're implementing the particle filter. So here we just have a really simple example. We actually just have a map here with one background, and then we just have some lines that we actually want to follow, and then we just track it like pixel wise. So we're just trying to have a box in a pixel with with the same background, and then we just want to localize that in our environment. So first of all here, we're going to import NumPy and also NumPy random here because we're going to initialize our particles here on our map randomly. First of all, we need to create our resample function, and our resample function takes in the weights. So this will be the weights of all the particles that we have spawned in our map or like in our environment. Then we just take n here, which is the length of our weights. So in here is actually like just the number of particles that we're going to use. Then we can set up some indices here, and then we can also get the C value here. So the C value here would actually like just be our like landmarks and the particles here that we're going to spawn. And then on top of our indices here will actually like be our new particles that has been updated with the weights. So here we're just going to sum up our different kind of like weights here. So we actually like get some value for like, we're just trying to find the good particles here or like the weights. So we're just going to create a new distribution with all the good particles that we found from our measurements. Then we basically just have a for loop here running through all of it. So we're just going to run through all of our particles, and then we just update our weights here or like update our indices. So we're just going to append here to its indices. And then when we have resampled here, we're just going to return our indices, and that will be our resampled. It would be a resampled particles that we can then spawn on the map again in the next iteration. So we take in the weights, we update our distribution of like where do we actually think that our robot is in. So this is actually like the main function for implementing the flowchart that I just showed you in the slides. So the particle filter here, it takes in a sequence. So in this example here, we're just going to take in a sequence of images. So we're just going to take in like 20 or 30 images, where each image is just like one sequence in the sequence, or like one instance in a sequence. Then we're going to set a position here. So this will be our initial position that we want to set in our environment. And then we want to track that down with our particle filter. We also need to set our step size here. So in this example, we're just going to set our step size equal to the maximum like steps that we can take within our sequence of images. So this is just a really simple example, but we need to choose a step size here. We could also like use the geometry here instead of our step size, but now we're just operating with like an image and pixels. So we're just going to choose a step size in this really simple example here. We're also going to initialize our function here, or we're going to call the function here with number of particles that we want to spawn on our map. So this is a really hyperparameter that you need to like try out on your own map and environment. It could be like 100 particles that we need to spawn, 1,000 particles, 2,000 particles, but the more particles we have, the more computational cost it will also take, because we need to take all the landmarks, we need to match all our new measurements with all those landmarks from our particles and so on. So it will just be more matching or like data association. But here we're just going to have our iterator here going through the whole sequence. And then basically here we just implement our particle filter as we have in the flowchart in the slides. So first of all, we need to set up our initial position. So we're just going to take our ones here from NumPy, and then we're just going to multiply that with the position that we set up here at the start. So this will just be our starting position or our initial position. Then we want to set up our toggle color model. So here, so when we're going to run the program, we'll have a blue bar in some place in the actual like the window, and then we want to actually like track that down with a box here that we have in the environment. Then we're going to return the expected position here, and also the particles and the weights, because we're using this particle filter. So the expected position is actually like a kind of like a prediction of where are we in the environment. We're also going to return our particles and also the weights. The reason here we're using yield instead of return is that we're going to create this generator instead of just like a normal function, because we're going to run this particle filter here inside like some kind of for loop. So we have a generator that is just returning stuff when we're actually like calling the function over and over again. So basically it is just because we want to run through this sequence here of images that we pass into our particle filter function here at the top. So down here, we actually like have our particle motion model. So here, first of all, we're just going to take a uniform step. So first of all, here we just have our for loop running through one image in our sequence. So again, we have a sequence of 20 to 30 images. We're just going to have its for loop running through all the images here in our sequence, and then we just have our flowchart here implemented. So first of all, we need to take our particle motion model here. We just set up np.add. Then we're going to take a uniform distribution, because we actually just want to have this uniform distribution when we're actually updating our weights. Then we're going to clip out of bounds particles. So if the particles actually like spawned outside of our map or like our environment, then we just want to clip out those particles, because we don't want landmarks outside of our map when we're creating that, which makes sense. Then we're going to measure our particles colors, because in this example here, we're just going to look at the colors of our particles and see where are we in the environment, are we close to where we want to be, and so on. And we're going to base that on colors, because again, we're just going to have like the same background. Then we have like a blue bar, and then we also have like a square that we're going to drag around, and all these three different kind of like shapes, they have different colors. We're in the example, so this is the exact same thing as in the example that I showed you. So these will be the lidar measurements from a robot in the example that I showed you in the PowerPoint. So here we're just going to take the measure of the particles colors. So basically here we just go in, take each of the individual particles, and then we just have the images here, or we just measure the particles colors. Then we get out here the F. Then we're going to actually take our weight here to the, which is act like the inverse quadratic color distance. So this is just like some metric to set up like how far are we from these two colors. It will be the same to take the distance from the lattice ranges from our particles and the lattice ranges from our robot. So this will actually just be taking or like updating our weights. Then we're going to normalize our weights, because we just want values between 0 and 1. And then we're just, so the particles with the highest weight will just have a weight of 1. So that we know that if we have a particle with weight 1, we are really sure that this is act like where our robot or like where our object is in the environment. Then we're going to return the expected position, the particles, and the weights, because we know this is just like an iterative process. So we're just doing these steps over and over and again. And because we're running inside of the sequence, we're yielding, so we can just get out the results. We can see the results while we're actually like running this code here, as we're going to see when I run the block of code. Then at the end here, we could just see like if the particle cloud degenerate. So we'll see that we actually like just get worse and worse performance. Then we're going to resample our particles according to the weights. So now we have a new distribution of our particles. Where are the good particles around in the environment? And then if we don't get more measurements, or like we don't get closer to our actual like object, then we're just going to resample our particles according to those weights. So say we have a particle with weight 1, then we're going to take that particle and then we're going to resample some new particles around that good particle that we found by doing this iterative process here, sequence, or like frame to frame. So we're just going to run this function here so we can use it later on. We're going to import PyLab here, itertools, time, and also IPython display, so we can actually display these images here when we're running our program. We just hit Shift Enter, import these modules. We're going to call iron here function, which is actually just for displaying what we're going to see. We're going to set up a sequence. We just have our image running through like some background that we define here. We're going to have 30 frames in our sequence. We're also going to add a square here with starting position x0. So this is actually like the square that we want to track down. We just set it with a starting position. And then we also have like an ending position here that we want to set up. So here we have a for loop where it's actually just running through our sequence here, or like setting these colors here for our XS here that we just set up here at the top. So this is basically just setting up our environment with the different kind of colors and shapes. It will make more sense when I actually run the program here, where you can see some different kind of objects with different kind of colors. We have like one background where we set up here. So here we actually have a sequence. We have an X slice and Y slice. So we just crop out, like we just slice our X and the Y values. I set those equal to 255. So here we're just going to run through our whole sequence here that we have. We're going to call our particle filter, which is a generator. Again, we're not returning our values. We're yielding our values because we want to see what is going on step by step when we run a function here. Or else if we're just returning, it will just call the function and it will not call it again. But now we're yielding. So here we're going to track the square through the sequence. We're going to see what is going on. So we just take our position. So P here is equal to position, XS, and VS, which is our weights. And then we can see our position overlay, zeros like the image. So we're just going to have zeros here for a position overlay. So basically, I want to go into details here. It is basically just for displaying what we're going to see when I run this block of code. The whole thing here is actually like up in the sequence. We just take a sequence of 30 images. And then here we just call our particle filter with our sequence, with our starting position, with a step size of 8. And then we're going to spawn 100 particles on our map. Down here, we're just going to imp show. We can set the colors here of our expected position. So where the blue line is actually like the expected position. And then we can plot the particles here. So the particles will actually be in red color. And then we're also just going to display here what is actually going on when we call this particle filter here on a whole sequence. So we'll run the block code here and see what the code does. If we just scroll down here at the bottom, we can see that the blue line is actually like where we expect the robot to be. We can see we want to track down this white square here that is moving around in the environment. And then we can see the red dots here is actually like the particles where we're tracking the white square here. We can actually see that our weights here, or like our particles, is actually lagging a bit behind our square here, but again we still track it really nice here frame by frame. Again, we only have 30 frames, but here we can see over time we actually gets closer. So it could be in 2 different positions. Our robot could actually be around here, and also down here at the bottom we have 2 blue lines, but we can actually see here that our particles is actually like tracking really nicely our square here around in the image. Again, our landmarks again is just our colors. We're just updating our weights based on the colors that we see. And then we just resample our particles over and over again, as in the flowchart that I showed you in the slides. So this is basically a really nice example. I'm just going to run it again here so you can see what is going on. We see we spawn our particles for each of the frames here. We're running through our sequence. We actually like update the whole or like all of our particles here with the associated weights that we gave them, or what they saw from the color differences that we set up in our particle and our resampling function of above. So thank you guys for watching this video here, and remember to subscribe button, bell notification under the video, and also like this video here if you like the content and you want more in the future. It really helps me and the YouTube channel out in massive ways. So thank you guys. I'm also doing a computer vision tutorial, so if you're interested in that, we're talking about like basic image operations, camera calibration, stereo vision, how to get depth information in our scene from stereo images, how we can create point clouds from stereo vision, and so on. So we have a lot of cool stuff within computer vision. So if you're interested in that tutorial, I'll link to it up here, or else I'll see you next video, guys. Bye for now.